on this. Now, once this is clear, what is the very first step in the power series method is that we have to assume the solution. That's what I'm writing. So if the problem or if the statement of the problem is saying that you solve this particular differential equation using power series method, then what is your first step? Your first step is that we assume that the solution will look like a power series. That is your first step. Now, how the power series will look like, that's what I'm writing, a0 plus a1x plus etc. And it goes all the way up to infinite number of terms. So therefore, because of that idea, what we have to do is we are supposed to substitute this yellow color equation into the given differential equation. So we are going to substitute. Now, if you want to substitute, what happens is there is a y double prime, but we don't have y double prime till now. We have only y of x. This means we have to differentiate the yellow color equation 2 times. So let us therefore finish the job of differentiating it twice, and after that we will substitute into the given differential equation. So that is the plan now. So let me therefore differentiate now. So this summation, when you are writing, we have to start from 1 only, not from 0. So that point should be important because the first term is gone to 0. You don't have this term now, correct? In case if you unknowingly put a 0 here, then entire thing will go wrong. So there is no need to worry about the next step. Right away you can say that you made a mistake. Now you see that we have to start from n equal to 0 onwards, because the 0th term, what you call the a0 term, is present. Equation looks like, it looks like this: 0, 1, 2, 3, 4, etc. And therefore an x to the power n will appear there. So that is how you write here, an into x to the power of n. Derivative n times, this is n times an x to the power of n minus 1. This is because of the differentiation, it appears like that. I want to rewrite this particular summation in such a way that n equal to 0 is coming here. This n value I am reducing by 1. You see that n value is 1 here. 0. How 1 becomes 0 means I am reducing 1. Now because I am reducing 1, you increase the 1 here. You increase the 1 here. So the n will become n plus 1 here. That's what I am writing. So that will become an n plus 1. Now you see that this becomes n plus 1. An becomes an plus 1. And n minus 1 you increase by 1. So this becomes n. Now what is the advantage is the yellow color expression here and the green color expression, both of them have common n equal to 0. And therefore when I am doing the summation, I can take it common. So that you can understand that this corresponds to the y prime of x. So which means that what is our conclusion? We have the given y of x here, or where our solution actually, and then we have the first derivative. But however, first derivative is not there in the given differential equation. Only second derivative is there, which means that we have to perform one more differentiation to the green color expression. So, and therefore we will be getting y double prime of x will be, so this a1 is also going to 0. And what will happen to 0? Now how much you have to add means 2 times you have to add. That's what I am doing now, right now. That will be equal to y double prime of x. So it is clear. Now it is clear that n equal to 2 is converted to n equal to 0 means I am reducing 2 numbers. 2 becomes 0 means reducing 2. To compensate that, you increase this number by 2. So n becomes n plus 2. N minus 1 becomes n minus 1 plus 2. Similarly, n becomes n plus 2, etc. So all these things. And finally, this is our result corresponding to the second derivative. So we got second derivative, we have first derivative, and of course we have the y of x without any differentiation. So now everything is available. We are ready to substitute all these things into the given differential equation. So let me therefore substitute into the given differential equation. So given differential equation we write once again so that it is easy to remember. Okay. So now what we are doing is simply I am copying. You see this, whatever green color expression is there, I am copying and putting it here so that you don't have to worry from where it is coming, because just now we evaluated the y double prime here in the green color. Similarly, this is a y. Y means without any derivative. That is our original assumption. I think it is in yellow color equation. So that you substitute now. So I'll bring that entire thing and then copy it here, and that is equal to 0. So I explicitly put some bracket here and then showing, so that y double prime is the first term showing this bracket, and then y will be this bracket. Usually brackets are not required, but if you put the bracket, it will be comfortable for you, and you can see that uh, each term corresponds to that quantity. So that is the meaning of that. And once we have this kind of common n equal to 0, remember common n equal to 0 is that. That is an advantage. Otherwise, you cannot compare. Now I am saying that we are going to compare the coefficient of x to the power of n on both the sides. I think this is not t to the power n. I am writing something mistake. We are writing x, right? So these things are x to the power n actually. I'll change it. Okay. Now, what is the next step is that these are all x to the power n that we are going to write down. So in this case, what is the next step is that we are going to compare the powers of the identical power. So what is the identical power that you are having? X to the power n is the identical power. Sorry, uh, this is going to page down. Okay, this step let me explain first of all, then we can come back. Now, only if you have identical powers of x, then only you can compare. You see here, x power n, you have x power n. Only when you have identical powers, only then you can compare. If one of them is x to the power n, if another thing is x to the power of n minus 2, then we cannot make any comparison. That is the reason. That is the reason why we have written down the green color summation. I have specifically shown in a different color, right? The reason is that the green color summation notation makes sure that this is also n equal 0, that is also n equal 0. By that, there is something happening indirectly, that these powers are becoming identically same, x power n. Because of that reason only, now you are able to compare. Otherwise, you can't do this step. Okay, so now if you are going to comparing means, what is the meaning of comparing means? You'll have to understand like this. There is a 0 here, so you put an equal to and put this on the right hand side. That is the meaning of comparing. If you are comparing something, you compare with the left hand side and right hand side. Usually that is how you say comparison. But right now 0 is there, so don't think that we are comparing with 0. Instead of that, you take this entire expression and put it on the right hand side. Then what is the expression? Then you will be getting negative of the summation of this quantity. Then compare what is there for the coefficient of x to the power n. So that is the reason why there is a minus coming. Okay. So if you compare what is there, n plus 2, n plus 1, then into a n plus 1, the entire thing, that should be equal to, since it is going to the right hand side, I will be getting a minus of the an. Now the question that you'll get is that what happened to all the summation? Totally summation symbol is gone, isn't it? So what is the meaning is that it is not that summation symbol disappear. Instead of that, we are going to say that this kind of expression is valid for n equal to 0, valid for n equal to 1, valid for n equal to 2, etc. Now that information is what is there in the summation, n equal to 0, n equal to 1, n equal to 2. So if you are going to substitute n equal to 0, then we are comparing x to the power 0 coefficient. So this much information is there in this line actually. That's why I'm explaining. If I substitute n equal to 1, then there will be an x power 1. So x power 1 coefficient will be given by this. Similarly, x power 2, x power 3. So this statement gives you all coefficients. So this is not a single coefficient. That is the point. This is not a single coefficient. So that is why we are saying that n equal to 0, one set, n equal to 1, another set, n equal to 2, another equation. Like that, you have infinitely many relations are there. Therefore, this is not a single coefficient. Remember, this is the coefficients of several powers of the x, where the powers are given by x power 0, x power 1, x power 2, etc. So now that you got this expression, there is a name for this expression, and it is known as the recursion relation. So I'll write down after doing one more simplification. So that will be equal to minus an divided by. So you put it divided by, you get an n plus 2 into n plus 1. Okay. So that kind of expression is known as the recursion relation. I'll explain what is the reason for that. Now if you see here, there is an an plus 2, there is an an here. Now, let us forget about the name. What is the use of this equation? If you think like that, what is the use? We can easily imagine. Our understanding is like this. If you somehow know, it is, remember, somehow, okay. If you somehow know the value of an, then it is possible to get the value for an plus 2. An plus 2 means the second term. You should remember that if this is a0, put n equal to 0 here. That if it is a0. If n equal to 0 is there, a2. So a0 and a2. So where is a0 and where is a2 in our power series? That is your second term. So a0 is the first term, a1 is second term, a0 is third term. So that means these are connected, right? One coefficient is connected to the other coefficient, and you can repeat this by substituting 0, 1, 2, etc. It is not a single relation. Once again, n equal to 0, one relation. N equal to 1, put n equal to 1 here, put n equal to 1 here, put n equal to 1 here. So then it is another relation. Like this you keep on repeating, then it gives you a set of all relations, and therefore this is known as a recursion relation. Recursion relation means one relation will generate several relations. That is why it is called recursion. Okay, so now we are going to practically substitute this n equal to 0, 1, 2, etc. And then we are going to get the values. Now, which are the things which are very important is that writing down this is very important. N equal to 0, 1, 2 is very important. You have to transfer this information here. Suppose if you forget to write n equal to 0, 1, 2, 3, etc., you do not know what to substitute here. Okay, it appears to be simple, but if you don't know, or if you forgot to write n equal to 0, 1, 2, etc., then you do not know what number should be substituted for the n. Do you want to substitute 3 first of all, or do you want to substitute 0? Where do you want to start? Or sometimes it may be odd numbers like 135. We don't know whether we have to substitute 135 or 246. What kind of number to substitute? So that has to be transferred from the summations. Very important. That is why I am writing this explicitly, and this must be written down, otherwise this recursion relation is totally useless equation. Okay, so now that you know what are the numbers to substitute, now we are ready to substitute n equal to 0. Okay, let us start with n equal to 0. Okay, it looks so simple, right? N equal to 0 is substituted, that becomes 0. This is 0 plus 2, 0 plus 1. So that is that number. So I get a minus a0 divided by 2. On the left side you have 0 plus 2, so a2. So that means I actually got the relation between a2 and a0. So that means I got one coefficient, that is the meaning. So now you understand what is happening. The power series method is a method in which we have to determine the coefficients in the power series. That's all about it. Determination of the coefficients of the power series is what is our job. If you determine the coefficients, well, that's all. We have finished the calculations. Now, therefore, we have now completed the calculation of one coefficient. Similarly, let us do the another coefficient by substituting. Next value, what is the next value? You see here, 1 is there. Therefore, n equal to 0 becomes n equal to 1. So now we will substitute n equal to 1. So let us do that substitution. That's all. So that corresponds to n equal to 1. Then once n equal to 1 is over, we can move on to the n equal to 2 substitution. Everything is similar, but we have to do the substitution. Otherwise, we don't know what the values will come. Minus a2 divided by, not a1, a2, right? Minus a2 divided by 4 into 3. And there is one small substitution we can simplify. You see what to do now. This 3 into 2 is there. We are going to make some arrangement so that this appears in the factorial notation. There is nothing wrong in saying 3 into 2 into 1, and therefore it is equal to 3 factorial. And later we will say that this is also 2 factorial. Okay, if it is the case, the other things also should follow like that. Okay, only then it is meaningful. That is fine. And what about this? How to simplify this expression is, there is a a2 here, but that a2 is already calculated here. It's there here. So why don't you substitute a0 by 2 with a negative value and then put it here. So put it here. So if you do that, then we can simplify it further. So I'll substitute that minus a0 by 2. divided by 4 into 3. Now you can simplify it as a naught divided by 4 factorial. And similarly, we have to do, of course, similarly, we can substitute with n equal to 3. And now let us put back the a3. Remember a3, this a3 is there, right? That's what I'm substituting. Divided by, you have 5 into 4. And that's all. So remember, whenever a3 comes, that a3 is already there. So that value has to be that this number, minus a1 by 3 factorial. So that is what exactly is coming here and then substituting here. So whenever known quantity comes, that also you substitute and then simplify. And we need some terms like 0, 1, 2, 3. You have to calculate some 5 or 6. Otherwise, writing infinite series is not easy. You need first few terms of the infinite series. Okay, first few terms can be something like 5 terms or 6 terms. You have to do only by doing 2 terms. It is totally inconvenient to write down the infinite series. That is why this kind of steps has to be executed at least 5 terms or 6 terms. Only then it is possible. Okay, that point you remember, and therefore the idea is therefore clear that we are going to write down n equal to 4 and n equal to 5 and so on. At least you write down few and afterwards you can write down and so on. Actually, this becomes minus a naught divided by 4 factorial. Then we have a divided by 6 into 5, and then we can simplify this, minus a naught by 6 factorial. That's all. And similarly, you can do many more terms. And once this is clear, now let us rewrite, let us collect all the summary. We have finished our calculation. In principle, we have completed. I want to now collect. Collecting means what? You see here, I am simply rearranging our result. In what way I am rearranging is 2, 4, 6, like that I am rearranging. And similarly, we will rearrange the odd number of terms here. So I'd like to write down that. Okay, now if you want to write down, let us finish this and go back there. So this is 2, 4, 6. But we didn't calculate 8, 10, etc. So therefore, but however, we will be able to write down what will happen if it is a 2n, because 2, 4, 6, right? Therefore, this is 2n. Now, how do you understand the series? You have to understand the series. There is a minus, then a plus, then a minus, after that plus. So alternating plus minus is there. So alternating plus minus is what we write minus 1 to the power n. Minus 1 to the power n means alternating positive and negative. That's all about it. Then afterwards, what is there? A naught, A naught, A naught. Oh, all the time A naught. Therefore, put the A naught there. Then after that, divided by, here what is there? 2 factorial, 4 factorial, 6 factorial. Then next will be 8 factorial. Then what will be here? This will be 2n factorial. That's what I am writing. Therefore, this is actually 246. Therefore, 2n. Then the whole factorial you put it. So that means, what is the meaning is that in general, we are actually telling all the even coefficients like this. So even though we calculated 3 of them, now we are able to tell the entire series. But however, only even number of terms. What about the odd terms? So let us write down odd terms. I'll change the color so that odd terms will be in another color. Let us say 3. We have only 3, 5 and 7, etc. So whatever we have only I am writing. So minus a1 divided by 7 factorial and so on. So if it is the case, what will be the... Now remember that this we cannot write down nth term. And you should also remember what is the point in writing 2n plus 1. See, if this is 2, 4, 6, then this is 2n. If it is 1, 3, 5, 7, then it will be 2n plus 1. In fact, you remember that we don't have a1 itself in our calculation. In our calculation, our calculation starts with 3 only. 1 is not there. Therefore, it starts from 3, 5 only. Now, how do you start with the 3 is because of the 2n plus. Otherwise, you can't start with the 3. So there you have to be careful whether to write n plus 1, 2n plus 1 or 2n. So that part should be clear. The series 3, 5, 7 will come only if you write 2n plus 1. Then plus, minus, plus is alternating. Therefore, I put a minus 1 to the power n. Then all the time you have a1, 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 and that is also fine. And coming to the factorial as usual, 2n plus 1 factorial, because it is the same 357 here also it comes, therefore 2n plus 1 factorial. So now it is clear that we have generated all the even coefficients, all the odd coefficients. So if odd coefficients and even coefficients are there, it means you have every coefficients in the power series. And that's all. Now that you have to write down only the conclusion. So let me therefore write down what is our final conclusion therefore. So this is so what is written here is our original assumption. Remember that this is your assumption. Assumption means this is what you assumed that the solution of the differential equation will be looking like this. But however, this can be rewritten in a different way. What is the different way is this contains all the terms. Now I am going to split all the terms into only even terms and only odd terms. So even term plus odd term will be the total terms. That's why I am splitting. Now why do you want to split is because we got the coefficient like that. It is not that we want to split. We don't want to split actually. But however, the coefficients are coming like that. Some even terms are there, some odd terms are there. In that way only the recursion relation came. And because of this reason, we are splitting this particular expression into two parts. One containing all the even terms, another containing all the odd terms. And that's the meaning. And once we have this, we can now substitute here. Now what do you want to substitute? You remember a2n here? This a2n is given by that expression. So you copy this and put it there. And similarly, there is a a2n plus 1 here. But a2n plus 1 is given by this expression. So you take this expression and then put it here. And that's what you have to do. Once you do that, we have actually found out the solution. So we are coming to the end now. So let me therefore write down. The final solution will be like this. I am simply copying this one, this particular thing. Then that's all over. Then plus I'll put some brackets so that it looks nice, and that's all about it. Now as you can see that in this expression we have only substituted this. There is nothing to simplify. In fact, once you finish this, your job is over. We can say that that is the solution. We don't have to do any more simplification. If it is possible, you can do. But generally, there is nothing to do with this, and we say that this is your final answer. So when we say the final answer, remember, what do you mean by the final answer? Of course, here is a point that you'll have to be you have to be careful. What is the meaning of this is that yeah. So now we are going to say that this kind of an infinite series that is written down with the two big summations here, we are going to say that it is the final answer. Answer to what? Answer to the y double prime plus y equal to 0. To that equation only. So you have started with the simplest differential equation, right? For that differential equation, the solution looks like this complicated summation that you have this, right? So whatever that you have, this kind of summation plus that will be the that is the solution. But the point that I would like to tell you is that you already know what is the solution to the differential equation, namely a cos x plus b sin x. So the simple looking solution, that is how you have, but right now it is looking very complicated. So you get a doubt whether the two solutions are really the same solution or not, or you made any mistake. So if you just want to think like that, then you can easily verify whether we can simplify this, and that's what we are going to see, that you can easily identify. You're going to identify that the first term is nothing but the cos x term, and the second one is nothing but the sin x term. Now, how do you know that? Means that is what I told in the yesterday's or the last class beginning. You should remember what is the Taylor series for cos x. Taylor series of cos x is nothing but this entire expression. Taylor series of sin x is this expression, because This is in the summation notation. In the last class we have written without summation notation. That means we say that x minus x square by 2 factorial plus x to the power 4 by 4 factorial. Like that we have written without summation notation, and now it is written with the summation notation, so that it is little bit more compact. So ultimately the point to be noted is that we are getting the same solution, and in fact you can ask the question, where is capital A? Capital A times cos x plus capital B times sin x. That was the solution, right? And of course that is there here, A naught. So it is appearing as A naught. Remember that in the summation A naught is constant throughout. Therefore this A naught will be staying outside. So that will be the capital A. Similarly A1 is the another constant. So that A1 will be a capital B. So ultimately what we are understanding is that the power series solution would be the identically same solution to whatever solution that you get by some other technique. Okay, the so-called auxiliary equation method, you already know that the solution comes. The same solution only we will be getting back. Of course, the solution to the differential equation will not change because of the power series method. But then I already told you what is an advantage. If that is the situation, why do you want to use the power series solution method? Is that we will use the power series method only if the simple techniques doesn't work, or the simple techniques fail miserably. In many of the situation it happens. So it is not that we want to use the power series solution deliberately. Okay, if the method of integrating factor is working fine, we don't want to use the power series method. That's what I'm trying to say. We will come to the power series method if and only if the simple techniques which are all known to us, if all the methods fail, and if you don't have any other option for you, then you come to the power series method. And power series method is reasonably powerful. Okay, the reason why it is powerful is you are going to use the infinite series, and the infinite series may not be easily identifiable. You may not be identified like cos x. See here, in the present situation, what happens is, in the present situation, it is so simple that this particular term can be identified as cos x from your standard Taylor series. If you have a table of Taylor series with you, you can easily identify this term is cos x, that term is sin x. Okay, but this kind of identification, if you are going to have a power series, you may not be able to identify to a particular function. Suppose if it is a sine square 2x, or if it is cos cube x by 2, that kind of power series you cannot identify directly. And similarly, suppose if you have a multiplication, suppose x square into sine square 2x, where is the Taylor series? You don't have ready-made Taylor series for that, and therefore you may not be able to identify. The point is that we are not interested to identify what is the function, but rather you simply leave it as a power series and say that that is a final answer. You see here it is written like that. You see that there is a power series that is written one summation plus another summation. Each summation is infinitely large. Okay, and then we say that is an answer. Now writing down identifying cos x and sin x is not at all required. In many cases it is not possible. Therefore, because of this reason, remember that whatever the power series that you are getting at the end, you say that that itself is the final answer. There is no need to further simplify and identify to some expression like tan of 2x, etc. Okay, that's not required and not possible also practically. So now what is the point that you learned is that you know how the method works. Okay, method is quite simple, that you are going to assume a power series of a particular form like a n into x to the power n, and then substitute back, and you have to do some algebra. And what are the places where you have to focus your attention, like the index has to be n equal to 0, and then the coefficient of x to the power n should match in all the terms. Only then you can simplify. Otherwise this algebra you cannot do. So the places where you have to focus your attention, those places I have explained with a considerable amount of time. Now when we are going to move on to the next differential equation, such as the Legendre differential equation, in the next class, I will not be explaining, or I will not be emphasizing more time in saying that maintain the power of x to the power n identical, make sure that the index n equal to 0 is identically same. So those points I will not focus attention, but instead we will see how to rearrange the algebra and then get the solution. So that will be your next step in the tomorrow or the next class. Mostly we will take up either the Mostly we will take up the Legendre differential equation, because that is the immediately it will be in the vicinity to this particular today's class. So okay, so that is the today's plan. So with this I'll close, and as usual, any doubt, any questions that you have, please write down in the comment section. I'll try to answer as much as possible. Okay, thank you.